Let me start recording. That's very ominous. Today we have the special treat of hearing an undergraduate seminar virtually. This is the second undergraduate seminar that's virtual, and it's been given by the wonderful Shaunak Modak. Shaunak's going to talk to us today. Well, he's doing something a bit avant-garde. I think a lot of times people give seminars about things that they've very, have been working on for some amount of time or been but Shaunak is giving a seminar on something that he's going to work on during the summer via the SURF Fellowship with a theorist in astronomy, Changpei Ma. Make sure to ask Shaunak a lot of questions, and take it away, Shaunak.
Okay, cool. Can you guys see the screen? The slides? Yeah. Okay. Well, hi everyone. My name is Shaunak. I will be doing the SPS undergrad seminar today on supermassive black holes and galactic dynamics. So I guess the first question is just, what is a black hole? So the technical definition, I guess, is a space in which gravity is so strong that light can't even escape. So you see a lot of drawings of them that look kind of like this, where there's kind of like this ominous empty black blob in the middle. That's like what the black hole is. And then you see kind of these warped views from gravitational lensing of the surrounding stuff. A definition that we're going to use more is that it's a compact mass M contained within this special radius, the Schwarzschild radius. So really it can be any mass M. Like we think about them as being really big, or maybe at least star sized and stuff, but it can be any mass M. Every mass goes along with the radius, for which if you squish that mass in there, then it becomes a black hole. And so black holes, like the above picture shows, are black. I mean, they're named because light can't reach us, and we really rely on light to take all of our astronomical observations and translate it into science. So instead we really learn about them through their interactions with other matter. So this picture on the left here is for a typical stellar mass black hole in a binary system. So this blue object is another star, and then the tiny object here with this big accretion disk is the black hole in question. And you can see that it's accreting matter into it from its companion star. So that's a common way that they increase mass, and a common way that we see them, because we can observe this brightly lit star, like the companion star, changing, and then infer properties about the black hole. And also we can observe them through these jets that are shot out of them, which I can talk about a little more later. Another thing that we can learn, another way we learn about them is by looking at that accretion disk in particular. And this is a pretty famous image. You guys might have seen it from last year. It's all over the place. It's the image for the Event Horizon Telescope. And it was made using observations in the radio band. And this bright stuff you see around it is the accretion disk plus copies of it lensed around, like the top image shows. And then in the middle, you'd expect to see a black hole. So in this talk in particular, I'll be talking about supermassive black holes. But before that, I want to talk a little bit about the more common regular kind of stellar mass black holes, so that we can get a feel for I guess the differences between them too. So a stellar mass black hole, this is just a pretty standard stellar evolution diagram. You can see the black hole in the bottom right corner of this diagram. So you start off with, well, a nebula here, they say, but it's just any region of gas. That gas collapses into a star, and we have the star evolving on the main sequence and as a giant star. And then ultimately, if that initial star is large enough in mass, rather than kind of fizzling out like this top evolution line and becoming a white dwarf with this planetary nebula, instead we get that the star explodes in spectacular fashion. And then what happens is a lot of the mass of that star is blown away just in stellar wind, or just, well, yeah, I don't know exactly what you'd call it, but it's just blown away as part of the explosion. Then depending on the mass of the star that exploded, you can either end up with a neutron star or a black hole. And typical threshold for it to go through this like supernova pathway instead of this fizzling out pathway is around 8 solar masses. And then maybe this black hole pathway, you start around like 10 solar masses. If you have like all of those right conditions, then you end up with this stellar mass black hole. So some characteristics of stellar mass black holes. They have a mass of typically around 3 solar masses. And then you expect an upper bound of less than 100 solar masses for sure. Typically, like the largest ones we've seen are in the tens of solar masses. I guess you might be questioning that 3 number. And the reason for that is, like I was saying, you need like 8 to 10 solar masses of the like main sequence star in order to become a black hole. The reason this number is much smaller is because a lot of that material is just lost, like ejected as a part of the supernova explosion, or in stellar winds as the star grows. So we expect an upper bound of 100 solar masses because, of course, if you start with a much larger star, even if you blow some of that material away, you still end up with a larger black hole. So they're found all across the galaxy, all across all galaxies, I guess. They're really dependent on star formation because you need a really, really large mass star in order to reach a black hole. And it's just, it comes out of statistics, I guess, but more low mass stars are formed than high mass stars in any star forming region. They're often found in binary systems, as these pictures on this slide and the previous slide show. The way we observe them is through jets, like the thing kind of coming perpendicular out of the accretion disk. Micro-lensing events, which is where they warp the stuff behind them from gravitational lensing. And then, of course, companion interaction, when they draw material from the companion, or even just like pass in front of the companion or behind the companion, obscuring it or brightening it slightly. So now on to supermassive black holes. So some of their characteristics, they have much, much larger masses. They're on the scale of like hundreds of thousands to like billions, even tens of billions solar masses. Whereas the stellar mass ones were, remember, less than 100. So they're found in galactic nuclei. Rather than being like randomly scattered in galaxies, they're found like directly in the center, and we don't really have good evidence to show that they're found anywhere else. So the observations for them are similar. We still observe jets from them. This yellow dot in the bottom image is actually a galaxy. That's the M87 galaxy. And this big pillar that's coming away from it is actually, it can be traced back all the way to the center, to the nucleus of that M87 galaxy. And that pillar is the jet that's coming out of the supermassive black hole in the middle. So observations of these jets were actually kind of some of the things that led people to think about the existence of supermassive black holes, because they were thinking like, okay, I see this like straight line in this image. If I trace it back, like what could be there? Is it like the same thing causing this whole straight line? In that case, it must be really big, really powerful, because the ejecta are reaching so far away from the actual galaxy, right? Yeah, so the jets are a big thing we can observe about them. And then we can also learn about their masses and some of their other characteristics through stellar dynamics and gas dynamics. And I'll be talking about that a lot more later, so I'll skip over it a little bit for now. And then I just wanted to go over some counterintuitive trivia about these supermassive black holes, because you might be inclined to think that they're like, oh, just like stellar black holes, except much, much more massive. But the qualitative behavior of them changes a lot just because of that much higher mass. So for example, you might think like, oh, black holes are like singularities, quote unquote, and like they have like infinite densities and stuff. But actually the like density of a supermassive black hole is typically less than the density of water, which I thought was kind of funny. And that density is just calculated as the mass contained in it divided by the Schwarzschild radius. The reason for that can be seen in the fact that the Schwarzschild radius, it goes as m, but then, so you take that mass and divide by the radius cubed, right? So you end up going, you end up with the density decreasing as mass increases. And then I think a common like sci-fi thing in black holes is like spaghettification. So formally, the way that works is when tidal forces, which means when you experience tidal forces that break up what's holding you together. So like a tidal force is when one edge of the object, like maybe your head, experiences a different gravitational force compared to like your foot. So like the strength of the gravity is so much that like your head and foot are pulled apart because they're accelerating towards the black hole at different rates. And there's kind of a characteristic radius at which that tidal force occurs, or that tidal force is strong enough to break apart like a typical object. And that radius actually is inside the Schwarzschild radius for a very large black hole. So for the lower mass black holes, there's like kind of more of a spaghettification risk if you go by them, because the risk is still there for the supermassive black hole. But by the time you're able to experience that risk, you've probably experienced a lot worse. So, so yeah, it's some trivia I thought was interesting. Okay, so you'll notice that I didn't really talk much about the supermassive black hole formation. Like I just went straight to the characteristics, and that's because we don't really know a lot about what the formation, how the formation occurred. So I'll just go over a couple of theories we have for that. So one way is like you start with a stellar mass black hole, like 10 to 100 solar masses, and then you just have lots and lots of accretion. So there's some problems that you quickly run into for that. The first one is the accretion timescale. So I mean, a stellar mass black hole like it can only accrete and increase its mass by like so much, right? So even if we say that the stellar mass black hole started like shortly after the Big Bang, and they've had like the entire age of the universe to accrete mass, the mass difference sometimes still isn't enough to like for them to accrete that much mass in the time that the universe has been there. So like you can't just say that the supermassive black holes started as smaller ones and then accreted lots of mass. A big reason for that is just separation between stars. Like typically we don't have a stellar mass black hole that has like tons and tons of solar masses to accrete from, right? Like it might be in a binary system or something. So like even if we just approximate and say it accreted that whole companion star, it's still not enough, right, to reach like millions and billions of solar masses. So another problem that's, I guess, a little more subtle is just where are the intermediate mass black holes? So if we expect the stellar mass black holes to become supermassive as a result of all of this accretion, we should be able to kind of look back in time, like look at like higher redshift objects, like farther away from us, and kind of see stars like in that process, right? Or black holes in that process. And yet we don't really see, or we haven't yet seen at least, any black holes with these kind of intermediate masses, like 100 to 100,000 solar masses. We only see like stellar black holes, less than 100 solar masses, and these supermassive ones, which are on the order of millions or more. So one proposed solution to that, like problem 2, is that those intermediate mass black holes are forming in these really, really dense regions of stars called globular clusters, or a couple of these other regions. And I can talk more about those at the end, but just know that there's a proposed solution. So like the proposed solution for globular clusters is because, first of all, it's very hard for us to see into the middle of the globular cluster. It's very, very dense and bright, and it's hard to resolve individual stars. But we can use dynamics there, so we can look at how the stars are moving and try and infer the existence of a black hole. And also, like all those stars provide plenty of source material, so perhaps the accretion kind of method could work in a region like that. So another kind of stellar-like way that these black holes could form is through direct core collapse. So the same way like that greater than 8 to 10 solar mass star has a core collapse, it has like a supernova phase, and then you end up with a black hole as like a remnant. In that same way, maybe there's a way for a really, really massive star to just directly like core collapse, like undergo the same kind of evolutionary trajectory and just end up with a really big black hole. So we're talking about extremely massive stars, like much more than hundreds of solar masses, thousands and more. And then the issue with this is that these really massive stars, as part of their evolutionary track, at least as we understand it now, they undergo a phase where they like emit a lot of stellar wind, which is just when they're ejecting a lot of mass and energy in the form of radiation away from them. So you can kind of see this in the bottom left picture. There's a bright star, and there's kind of this arc in front of it. So that arc is a result of wind from the star interacting with the interstellar medium, which is like this cloud of stuff on the right side. So that's just, I don't know much about fluid dynamics. I can't really talk much about that structure, but that's evidence of stellar wind. And then also we have, of course, mass loss and explosions. So it's hard because the stars are losing a lot of their material. So you need really, really big stars if you want to end up with something supermassive. So one proposed resolution to this problem has to do with these special stars called population 3 stars. So these stars are the earliest forming stars in the whole universe. And the reason that these stars might lead to more support for the direct core collapse model is that it has to do with star formation. So this diagram here with these blobs and arrows is a rough way that we think stars form. So you start off on the left side with this big cloud of blue gas. And what happens is a process called fragmentation. So this big blob kind of separates into smaller ones, and those ones separate into smaller ones. And so multiple stars form from this really big blob. And you get a bunch of small stars rather than one really, really big, really massive star. But if you have a sufficiently old star in the early universe, there was mostly just hydrogen and helium, because a lot of the other elements came from they came from stars, right? From fusion in stars. So if you have like a sufficiently pure gas, then you can have a situation where like this entire cloud forms into one single star without having too much fragmentation. And this is only popular in those older population 3 stars, like some of the first stars that ever formed, because of that purity kind of requirement. So some people say that it's possible for those stars to have undergone kind of a core collapse situation and become supermassive black holes, or at least start off with an initial mass that allows them to more feasibly accrete stuff to become supermassive black holes. So that's kind of one resolution. Another way that those supermassive black holes could have formed is through mergers. So this is one where you can take a couple of different stellar mass black holes, and then they all merge and lead to an intermediate one or a supermassive one. And we know that these mergers exist, as we have like direct detections of them from LIGO, which I'm sure you guys have heard of at least a little before. The image from that is one of the renderings of what we think that might look like. So we have two black holes kind of spiraling together. As they're spiraling together, they release a lot of energy in the form of gravitational wave radiation. So, I mean, very qualitatively, like ripples in space-time and stuff. And so that's something that we can observe. And we think that maybe if there were enough of those or mergers of sufficiently large ones, then it could lead to the supermassive black holes. Of course, they would have to have formed a lot earlier in the timeline of the universe, because we need them to be at the centers of galaxies, as we'll see. So this kind of fits well with one of the theories of galaxy formation, it's called the bottom-up theory. So it says that the galaxies themselves formed as mergers of smaller component galaxies. So like a galaxy as we think of it, like the Milky Way, maybe it's a result of 4 of the like galaxy fragment kind of things, all being attracted to each other by gravity, and then over some like long merger process in a long time, it became the like single galaxy that we see today. So it's plausible that maybe in each of those tiny galaxy fragments there was an intermediate mass black hole, and then in the process of the merger, the intermediate mass black holes all fell toward the center of the galaxy, like the resulting galaxy. And a merger between those intermediate mass black holes led to the supermassive black hole at the center of the galaxy. Yeah, so as I mentioned, the observations that we have for those are gravitational waves. One big question is the rate of those mergers that we expect to see. So in general, in astronomy, a rates analysis is kind of saying, if we expect like these processes to be going on, how many of those processes do we expect to be happening in the universe at any time? And then how many of those events that occur are actually observable to us? So if this process is sufficiently like easy to happen, like easy enough that we observe supermassive black holes in the centers of most of the galaxies right now, then how come we should be able to see it happening? We should be able to get a sufficient amount of gravitational wave signals, like and some number per year, let's say, of detections. So the rates are still in question for a lot of gravitational wave astronomy. Another thing is we need detectors across, need gravitational wave detectors across this wider frequency range, because it just like the way it works in general relativity is that the frequency of the gravitational wave depends on the mass of the constituent black holes. And for the larger and larger black holes, like the intermediate mass ones that would be merging to form the supermassive ones, for larger and larger black holes, it's lower and lower frequencies. And right now, LIGO only detects like a very small frequency range. So more experiments are being proposed to broaden that range so we can maybe get some more signals and see if this theory holds up. So the picture on the right here is a quick sketch of one of those proposed experiments that broadens the frequency range. So it's called a pulsar timing array. A pulsar is each of these like little dots with the beams coming out of them. They're interesting compact objects on their own. I'm not going to talk about them too much, but roughly what happens is they have these very, very fast rotation or precession periods, and they act like really, really well calibrated clocks. One proposed idea to see, like to measure more gravitational waves is by observing each of these pulsars, like using it as a local clock, and then checking like the time differences that we see between, correlating those time differences across different pulsars so that we can learn more about the gravitational wave in that way. Okay, so the last kind of way that people think that these could have formed is, it's a little bit of a cop-out, I guess, but it's kind of just saying, what if they were like always there the whole time? So primordial, in the sense that they formed shortly after the Big Bang, and there wasn't really any core collapse as such involved. It's like a direct collapse black hole, maybe. So directly formed from a gas disk, just like collapsing straight into a black hole, like skipping off the stellar phase. I don't really know too much about the physics behind that process, but I know this is like talked about as a very common way for black holes to form. And the reason for the reason that this collapse is allowed is due to these potentials that arise from like quantum fluctuations right after the Big Bang. So it's kind of like similar stuff that we would expect to see signals for in the cosmic microwave background or in other cosmology experiments. But basically those slight overdensities led to places where matter could easily collect and combine and collapse. So we just start off with these black holes. So you can predict a range of masses that's like really, really large. So that should be 10 to the 11 solar masses. Yeah, but so you predict a range of masses that's super low. Like it can go all the way down to 10 to negative 8 solar masses. I don't know if there's a clear upper bound easily visible, although I guess people would just say that the upper bound is the largest supermassive black holes that we currently observe. But the lower mass ones, again, that should be less than 10 to the 11 solar masses. Those ones decay away due to Hawking radiation. So over the timescale, like over the age of the universe, basically, they just decay, like losing mass energy to thermal radiation. We can't really see too many of these super small ones.
Shaunak?
Yeah.
Wait, so what is roughly this, like, how should I think about 10 to the negative 8 solar masses? Like, what is, like...
Ooh.
like
Okay, so let's see. The sun is 10 to the 30 kilograms, so 10 to the negative 8, that means 10 to the 22 kilograms. Yeah, that's a good question. I'm actually not sure. What I can say is that around 10 to the 25, around 10 to the 20 something solar masses, that black hole is like ball size, like basketball size. So 10 to the negative 8 is extremely small. It's like, well, I hesitate to say like atomic scale and stuff, but it's extremely, extremely small.
And to the 8
I don't know. Like I don't have a great
lunar
way to
mass.
Wait, sorry, what?
10 to the 8 is like lunar mass.
10 to the negative 8? Okay.
Yeah.
Okay, so I should think about these as moon-sized black holes. Okay.
In terms of mass, yeah.
Yeah,
in terms of mass, yeah.
Mm-hmm.
And therefore radius, right? Like the radius goes like 2m or something, right? Or of a black hole.
Radius goes like 1/3, right?
Wait.
Sorry, what was that?
Sorry, what?
the radius of a black hole goes like 2 times its mass, right? Or 2g
Oh,
times its mass.
yeah, except there's also a factor of g over c squared.
Oh
So
yeah.
yeah.
Yeah, okay.
Scaling, sure. Yeah.
Yeah. Okay.
Oh,
Yeah,
is there,
so Wolfram
is there a
Alpha
chat?
says 10 to the minus 8 solar masses gives a radius of like 10 to the minus 5 meters.
Jesus
Okay.
Christ. Okay.
Oh,
Micron scale, sure. Okay, yeah. I mean, I didn't know that. I don't really have good perspective on all of these scales, honestly. It's
Wait,
pretty
these are
hard.
cellular
to
black holes.
explain. Yeah.
Alright.
Okay. Yeah. So anyway, I was saying these black holes are the primordial black hole theory. It's a little bit hard to observe and a little bit hard to constrain. So in terms of constraints, it's tricky to have these like really small black holes like all over the place because we'd expect to see a lot of lensing events associated with them. And then, of course, like I was talking about with the rates for the gravitational waves earlier, we look back and we don't really see tons of mergers going on. So, well, we don't know if we have the precision to see that yet, but that's definitely something that we'll have to think about before we can accept this kind of theory. And again, the same kind of lack of intermediate mass black holes is still an issue here. But yeah.
Is there any understanding of how a primordial black hole would even form, like without becoming a star first or something? Like, because a moon-sized black hole, you're claiming like a mass the size of the moon somehow becomes a black hole. How does that even happen?
Yeah, so I think the idea is that you can get this like direct collapse thing. If there's a like steep enough like potential well that's due to like dark matter or something else. So like the story is the like quantum fluctuations lead to tiny like spaces where dark matter is super dense, and then if you have like a sufficiently dense area already, mass in there can collapse much more quickly. I'm not really sure about the details of that though. Yeah, it's definitely a good question to ask though. Any other questions about the like primordial black hole kind of idea? Okay. Yeah, a fun fact that I found while I was like looking stuff up for this slide is that some people think, so apparently some observations of the solar system suggest that there could be like a ninth planet kind of, a ninth planet-like object, except the big issue is we haven't seen it. So some people suggest that like that effect can be because of a primordial black hole that is like tennis ball sized or something like that. So I don't know, I thought that was kind of funny though. But yeah. Okay, so next, now that we have at least maybe some idea of ways that the supermassive black holes could form, I want to start talking about their role in galactic dynamics. So the first thing, I guess, is these active galactic nuclei. So this is a little bit of a like historical approach. So active galactic nuclei were actually one of the reasons like that people first thought that supermassive black holes would exist. So the story behind this is, so I guess first, an active galactic nucleus is the source of extremely energetic emission from the center of the galaxy. So right in that's where the nucleus part comes from. And we see like X-ray emission, we see like very, very strong radio emission. And originally we classified galaxies based on the spectrum of those. So that's where like a lot of those like fun vocab words come from, like quasars, blazars, liners is like, I wrote it down somewhere. Low ionization nuclear emission line regions. So I don't know, astronomers come up with great acronyms. But we came up with a lot of kind of separate looking objects because they all had very, very distinct spectra, like spikes in some spots, flats in other spots, barely any emission in the radio in some, a lot in another. So the supermassive black holes kind of arose as a nice unifying model to combine all of those objects into one. And this is really good because if you have a lot of these objects, then you have to come up with a theory for galaxy evolution or a theory for like large scale structure formation that says, okay, like I'm going to have a bunch of these separate objects, like similar in all ways except for what's going on in that nucleus, like arise somehow. But this way we can kind of see that it's like a galaxy as we expect with a supermassive black hole in the middle that's doing something special. So the idea of these supermassive black holes kind of like united all of those ideas. So this is, math was hard to do on slides. I didn't know how to write equations and stuff, great. but this is my attempt, and this is like the only math thing in this presentation so far. We'll pretend to be the observer at point O, and then we're going to be looking at like the object, the hypothetical object that's doing all of this energetic emission. So that object is centered at the center of that other circle on the right-hand side, and that object has radius r. So one thing that we can observe about that object is the timescale associated with the brightness changes in different things for that object. So the idea is we're going to get an estimate for its radius using like the light time travel, like that delay between the length L1 and L2. We can just define the difference in time travel between those ones to be delta t, and get that the radius of the object is going to be the speed of light times that time interval divided by the Lorentz factor gamma. Using like twiddles like we do in astronomy, we're going to call the Lorentz factor close to 1. The delta t for a typical AGN for measurement, it could be around an hour. Anyway, that's a reasonable scale. And we end up with a radius around 7 AU, so 7 times the distance from the sun to the earth. So I guess the first notable thing is that's a very, very small distance for something that's so energetic. So these AGN are like, AGN events can, like activity can lead to brightness that outshines like the entire Milky Way by orders of magnitude instantaneously, I mean. So this really, really compact object that's like it's just a little bit like it fits in the solar system, it is producing something so energetic, and that's surprising. So the next thing we have to bring in is this thing called the Eddington luminosity limit. This Eddington luminosity limit is kind of a maximum like luminosity that an object can emit when it's under hydrostatic equilibrium, which means the pressure and gravity are balanced, so it's like stable in that sense. So the calculation, the derivation for this, it basically includes like includes like radiation pressure, and then this number is a combination of like a bunch of fundamental constants, and then if we're radiating like charged particles, it's related to like the mass of the proton, like the Thomson scattering section. I'm not sure what else, but that's a number, and that's a scaling relation in terms of the mass and solar masses. So now we can calculate a lower bound on the mass using an observation of a typical luminosity. So with our typical luminosity measurement of like 5 times 10 to the 39 watts, oh yeah, this is following a derivation from a textbook. So that observation, I don't really have good citations from it, but they say that it's typical. Plugging in that typical luminosity, we get a lower bound of a mass of like 3.3 times 10 to the 8 solar masses, which is putting us at the scale for the supermassive black hole that we expect. Then the other thing that you can compare it to is just like reverse engineering like a mass from a short shield radius. So if we plug in that radius of around 7 AU from earlier, we get something that's very, very similar. If not numerically, at least the 10 to the 8 solar masses is right. So we have a plausible candidate for what could be causing the AGN, and it's a black hole with that sort of short shield radius. So this is, again, as I mentioned, kind of like the earliest evidence for the existence of these supermassive black holes. And now it's pretty much like well accepted that all AGN activity is due to interaction of the black hole with stuff that's accreting into it. And the different types of AGN activity can be related to, I guess, like different types of things it's accreting, and also other functions of the galaxy, like its age and luminosity and stuff. The next thing I want to talk about is just correlations between supermassive black holes and the structure of the galaxy as well. Lots of them exist. Most of them are not super well understood or explained. Some of them are kind of ones that you would expect kind of intuitively. Like the mass of the supermassive black hole is correlated with the mass of the galaxy. So if you have a really, really higher mass galaxy, you have a higher mass supermassive black hole. I guess I can kind of imagine that as just saying that the supermassive black hole has like more source material or something. It's not the best intuitive explanation, because you might say, oh, well, if the supermassive black hole is like consuming all of the mass in the galaxy and like, you know, radiating it as jets and stuff, maybe the mass should be lower. But yeah, I'm not sure. The mechanism for these are not at all like understood. There are a bunch of conjectures, but none that I could find like sufficient like community agreement on. Another one is that larger supermassive black holes are found in elliptical galaxies and spiral galaxies. We kind of expect this because elliptical galaxies are larger mass in general. They also tend to be older, and like some people think that they come from mergers of galaxies and stuff. That kind of makes sense to me. Then you get some correlation that like there's not even like a semi-intuitive explanation. For example, larger supermassive black hole mass correlates with higher like outer part of the galaxy stellar velocities. So I mean, keep in mind that the mass of the supermassive black hole, it's very large, but it's still localized to the center of the galaxy. Like the sphere of influence of the supermassive black hole is like fractions of a percent of the radius of the galaxy. And yet we see positive correlation between like stars in the very outermost regions of the galaxy and the mass of that supermassive black hole, which might indicate that it has some more role to do in the formation of the galaxy or the evolution of the galaxy. But again, the mechanism is not really well understood. So this type of correlation we call really, really good in astronomy, in galactic astronomy, I guess, even though it looks kind of like a mess. So this last one is perhaps the only correlation that we're starting to get a good sense of. And it's called the M sigma relationship. So it's the M is for the mass of the supermassive black hole, and then the sigma is the velocity dispersion. And in particular the bulge velocity dispersion. So this is a typical model of a spiral galaxy. The bulge is kind of this middle, thicker part in the galaxy. Then you can see like the disk and the halo and stuff. And for perspective, there's the sun's location. I think the sun is around 8 kiloparsecs from the center of the Milky Way. I guess units, it's hard to make those units meaningful. But the center, like the central bulge we're talking about, is maybe 1/8 of the way or 1/10 of the way from the center of the galaxy to the sun, for perspective. So that particular bulge, the bulge is similar to an elliptical galaxy. It's kind of like a small elliptical galaxy, just like in the center of even these spiral ones. So in the spiral arms, you can kind of see that velocities are a little bit structured. Like for example, they're all roughly in the same plane. The disk is pretty thin, and you know, like we see like the spiral movement. There's like density waves. All the stars are orbiting like kind of nicely in a plane like that. But in a bulge, it's more characterized by random motion, similar to elliptical galaxies. So rather than the absolute velocity of any given star, what we care about is the dispersion of the velocity. So dispersion is just a stand-in for like a statistical measure of spread, like usually like standard deviation or like interquartile range, like some measure of spread like that. So we care about that the dispersion of velocities around the mean there. And yeah, so that M sigma relationship, that graph over here, it's a reasonable fit. A lot of times you'll see like much more scatter on these plots, but this one worked out not too badly. And then a lot of people have proposed that fit means that there's some sort of feedback mechanism here, in the sense that we see this for a lot of galaxies, even galaxies that we know or we like strongly believe that should have had like mergers happening in them, lots of like collisions and events, like just like really, really weird galaxies. So because we see that so broadly, and we call this fit pretty good, we guess that there's some sort of feedback in the sense that the supermassive black hole like helps kind of like stabilize the galaxies, like velocity dispersion in the bulge, and vice versa as well. For example, in a galaxy merger, as the supermassive black holes are merging, then there's some sort of flexibility due to like I think the momentum transport in the gas of the accretion disks. Yeah, I don't know much about this either. I kind of learned about it earlier today as well. But like roughly, this is like one of the only correlation relationships where we actually believe that there is some sort of mechanism proposed. Yeah. Okay, so I guess the question is, how do we like learn things about these supermassive black holes, which hopefully I've convinced you are interesting / important. So one of them, which is like a kind of silly suggestion, but it actually works a bit, is just like look at them. So I mean, it's a simple concept. It works well for things that we can actually look at. for example, the Event Horizon Telescope, like that orangish blob black hole picture that I showed you in the very beginning, they're going to conduct this observation for M87, which was, if you remember, the galaxy with that big jet that I showed you earlier, and also our own galaxy, the Milky Way. And one issue with this is at the current effective, like, well, at the current technological level, I guess we have, those are basically the only two galaxies that we can learn about through this like direct observation method. So the Event Horizon Telescope it's a radio telescope. So a lot of chat. Oh yeah, okay. So a lot of things a lot of the ability of radio astronomy to resolve these objects is based on like a baseline, which is roughly like a separation between the two antennae we're using. And Event Horizon Telescope has those spread out all across the Earth. But it's hard to get a longer baseline than that. So unless we get some better ideas, so far those are the only two that are possible. So another thing that I want to point out is this video of orbits, which I think most people, like anyone who's taken like an astronomy class has probably seen, but I still think it's pretty cool. So this is for this like star position is kind of where our own Milky Way is, or our own supermassive black hole is. And what we can do with our own local area is actually measure the proper motions of the stars, like reconstruct the orbits from the motion of stars in the sky. So that's what's being done here. Each of those other colorful dots is a star, and by retracing these orbits of the stars, we can use Kepler's laws basically to learn about the like mass of the supermassive black hole. I think sorry, what was that?
Are we supposed to be seeing the video right now?
Oh wait, you can't see the video. Oh yeah, that's a big thing. Okay, let me.
Yeah, it's only on the screen, like your
Okay.
presentation.
Okay, can you see the thing now?
No.
No.
Yeah.
Okay.
No.
Oh, yeah.
Wait, yes, you can.
Yes.
Now we can.
Okay.
Not full screen yet, but yes.
Okay, yeah, not full screen, right? Can you see it full screen now?
No.
Yes.
Yes.
Okay.
There's a little bit of a delay.
Okay, yeah. Well, this is the one I wanted to show you. Like, we can track the motion of stars in orbits around this very compact object. So, I mean, what's going on is we can really constrain the radius in which that object must be, because all of these stars we see going around it, some of them are going really tightly around it. So we bound the region that object can be in, and then we use things like Kepler's laws to determine stuff from these orbital trajectories. And because of that, we can like confirm that there is some sort of supermassive black hole in the center of our galaxy. Can you see the slides now?
Yeah.
Yeah, okay. Yeah, so I don't know, I like that video. Another way that we can learn about the supermassive black holes is through dynamical measurements. So there's a couple of steps involved. One of them is to extract a velocity field or a set of orbits from spectra. I couldn't find any good images for this, so I just took like a screenshot of that video, but imagine this, except so this is super localized around the central black hole. Imagine like this, except like rotated 3D, like completely filled in, so like you couldn't even see those stars in the center. Like we want a velocity field that's like integrated over all of the like space that we're seeing. Even so, like much more, many more orbits than this. Okay, so the next step is to model the interaction of the gas or stars. So like modeling that fluid or the stars as point masses with the supermassive black holes. That takes really complicated simulations. If we want to do it with gas, it's really hard because gas, it's like it can be ionized and stuff. Then we need magnetohydrodynamics, and then that takes up a lot of time and energy. For stars, it's a little bit easier because we can just treat them as like point masses with respect to gravity. And gravity is like the only interaction that we really consider important there. And I guess the trade-off is the gas should give us like a fuller picture of the interaction, but the stars are much easier to do. So what we do is we basically conduct those simulations by placing, like we just drag and drop, basically like we put a black hole that fits our model into the simulation. we watch the orbits run a bit, and then we just say that the mass that we're going to say like that supermassive black hole has is the one that best reproduces like our observations. So a typical thing we can observe is a mass to light, is a surface brightness profile for a galaxy. So like in the picture, the galaxy kind of just looks like a blob, but it's brighter in some spots than other spots. So we say that there are more stars in that brighter spot than the other spot. What is this? Oh, okay.
Bye.
Goodbye. Okay, so we expect there are more stars in that bright spot than in the dimmer spots. And moreover, if that like kind of ratio is relatively constant, we expect that there are more stars in orbits passing through that bright spot. So not just a bunch of stars that are floating there. There are stars going around in circles or in ellipses, whatever, in orbits around the black hole, except more of them consistently pass through that region. So we come up with a couple of different ways to simulate those dynamics, and I'm going to be focusing on stellar dynamics. So the first is the n-body method. This is kind of like straightforward, like what you might imagine. You take a different black hole, you place it in the center of the galaxy, and you put in a large number of stars around it. You specify some reasonable initial conditions on their positions, like maybe their distribution is related to the brightness profile of the galaxy or something. And then their velocities, you can kind of like do randomly if it's an ellipse, or you want to obey some like angular momentum conservation or something if it's a spiral galaxy. So you just place those stars, you specify the conditions, and then you just like hit play, like let the interaction simulation do its thing. And then you wait and see if the end result after a while, like after a bunch of orbit times maybe, or like a sizable part of the age of the universe or something, see if that profile in the end matches the observations that you've taken. So the good parts about this are that it shows like kind of how that observed configuration of stars was reached, because you start off in like a relatively random situation, and then you can actually watch it converge to the observed profiles. So you can kind of see like the transient behavior in between, and that might be useful for looking at like galaxies that are interacting, or like if you're looking at like look back time, like higher redshift galaxies, like galaxies farther away from us. The con are obviously it's super computationally intensive. You have to model every particle interacting with every other particle. It scales horribly. So the other way that you can simulate the dynamics, which is what I am going to be working on, and I mean, everybody's been working on this for like 20, 30 years now, is called the Schwarzschild method. Actually, this Schwarzschild guy is like the son of the Schwarzschild radius guy, which I think is kind of funny. So he came up with this method in, I think, the 1980s. And then the first like computers got good enough to implement it in the 1990s, maybe 2000s. So the way this one works is you specify the entire gravitational potential profile. Rather than just putting like the black hole in the middle, you specify the entire potential as like a scalar potential. We're just working in Newtonian gravity here. So you specify that potential, and then you place a star in it one at a time to watch individual orbits. So you've started off with your potential. You put a star in, you watch a star go around in that potential, moving the potential for a couple of loops. And you do this for a lot of stars. And then what you do is you take superpositions of those orbits in order to reproduce the final observed distribution. So like I was saying with like the bright spot and the dim spot of an observed galaxy, what you do is you put a superposition of orbits so that you end up with, at any given time, a large amount of stars are passing through the bright spot, and comparatively fewer are passing through the duller spot. So the good thing about this method is that you don't have to do these like crazy amounts of interactions. You've already specified the potential, and then a star just has to move in it. So you don't have to worry about that star interacting with other stars or anything else. And I guess the way that you check that this method is viable is eventually you should find a configuration such that the stars, like the end result of superposition of the stars, reproduces the initial gravitational potential you guessed. So like you guess a potential that is going to be like the final potential that includes all the stars. So you kind of like skip this step of how that potential is reached, and you just say, if that potential was the final potential and I move stars in it, is there a way that I can take superpositions of those in order to like produce the thing that I guessed it would be? The good things about this are The good things about this are it's easily adaptable to different potentials. So like you can do potentials with different amounts of symmetry in them. Rather than doing just like a spherical potential, you could do like an axisymmetric one, like an ellipse looking one. You can even do like triaxial potentials, which is kind of the current like stage of research, is how do we adapt this to these situations that lack symmetry. And then of course it's computationally easier because you don't have to do tons of interactions. The cons are, of course, you can't really comment on the evolution towards the observed configuration. And it might take you a lot of tries to guess it as well. But a lot of like theoretical work is being done on how to best guess those gravitational potentials as well. Okay, so I guess as a summary, these supermassive black holes are interesting. We don't know much about them though. We don't really have a good theory of how they form. We have some explanations for, we have some support for their existence coming from AGN. And we know that they're important in galactic structure and evolution because of those correlations that they have with their host galaxies. The way we're trying to learn more about them so we can kind of firm up maybe the formation and the mechanisms for those correlations are understanding the lack of the intermediate mass ones, maybe through more gravitational wave signals, like better detectors, more interesting methods, and also finding their masses through dynamical methods, kind of just building up our database of observations and confidence. And one of those methods that I'm going to be working on later is the short shield method in stellar dynamics. That's all I have for now. Thank you. I can take any questions as well.
So let's all give a round of applause, question mark, to Shaunak. You can react, maybe that's fun. Yeah, there you go. Yeah. So I don't really know the best way to take questions. But if you have a question, I suppose you can just speak up.
Okay. What fraction of stars have solar mass or have a mass greater than 8 solar masses?
I don't know off the top of my head. There's something called the initial mass function that we specify for every galaxy. And actually it kind of boils down to our not great understanding of galaxy morphology. Because we don't really have a good way to classify all of the galaxies besides just like clearly spiral, clearly elliptical. Like we have ideas, but not a great way. So specifying that initial mass function is really important. And it depends on a lot on like the parameters of the galaxy, but not very many. In fact, like most stars are definitely less than a solar mass.
So in that case, it's unlikely that there are just like black holes everywhere that we're not seeing, and that's accounting for a lot of like unobservable mass.
Yeah, I mean, so like actually it used to be a common dark matter theory. Is like, what if there are just a lot of black holes like far out in the halos of the galaxies? But yeah, I mean, the rates part of that, I'm not sure, like the formation rates. But another thing is like if we had a lot of those, we would be seeing a lot of lensing events. So we'd be seeing microlensing, like brightening and dimming other stars, or we'd be seeing like larger scale lensing, just like warping the background. So we don't see so much lensing. So we kind of rule those out as like they're not as invisible as we think dark matter is.
Gotcha, thanks.
Are there any other questions?
Yeah.
Yes. Little, yeah.
You said about like using all the simulations to figure out like the evolution of the your configuration around the supermassive black holes. Is that, well, like as far as I'm concerned, it seems like that's only applicable within our own galaxy, right? So like how do you,
wait, which simulation?
Yeah, because no, I mean like because you have to sort of like confirm that with like observation as well, right? But you can't really resolve individual stars around like other supermassive black holes except for like say a star. So
so in other galaxies you can resolve like integrated line profiles is what they're called. So you kind of you just like better resolution is always better. But you just take you can look at a spectrum and you kind of integrate like over like a column of stars, like you're like looking through a bunch of stars. I'm not really sure, I can't really like draw this or find a good intuitive explanation, but the idea is you only need to reproduce like kind of like a rough velocity field, because that's going to inform your initial conditions. And then it's also, the idea is also you can just use surface brightness profiles. So what you do is you do a parameter sweep across mass to luminosity ratio, and also like the idea is you want to find how many stars are passing through any given region of a galaxy, right? Like in any time. So mostly you're just trying to reproduce those surface brightness profiles and also the spectrum of the galaxy.
Okay.
Mm-hmm. Yeah, so actually like this has been done for lots of galaxies. And I think in particular they do it for, it's been done a lot for elliptical galaxies, and kind of a problem, like the problem with the lack of symmetry that I was mentioning is because I mean, elliptical galaxies are not spherical galaxies. So that's kind of like the next step, so we can do this to more galaxies, just have a bigger catalog.
Yeah. Okay.
Interesting. Yeah, Eric.
Oh, so like in a situation where you have like a couple black holes merging, does the form that the like strength of gravity take change due to like I don't know, relativistic effects or something? Like, is it are the dynamics still like inverse square when you're working with black holes up close, or do things get weird?
Yeah, I'm not sure about the details. Like I like far away, it still looks okay. But up close, I'm really not sure. I think up close, you probably are like also like you really can't talk about like the forces kind of conception, because you have a lot of like, I mean, a lot of like in GR language, like off diagonal terms, right? Because like there's like all these gravitational waves, and the waves are stronger there too, so they contribute more. I'm not really sure about this though, actually. I think,
Yeah.
I guess in the context of like this, we're looking at large timescales. So we're like assuming all of that behavior has settled down, and we just like in the middle of every galaxy we observe, there's just one supermassive black hole. But yeah, I mean, I'm sure it has a lot to do with like evolution of galaxies, like in mergers and stuff.
Okay. I think that's all of the questions that are actually, I suppose we have as much time as we'd like,
Yeah.
but I should stop the recording right about now. So yeah, let's all give Shaunak one more round of applause.
Thank you.
Yeah.